Welcome to an edition of CCSD Living Environment. Today we're going to talk about the idea behind sex determination. How is it that male or female is determined in the embryo? And we also want to look at this concept known as sex-linked traits. How is it that there are certain traits that are connected simply to our sex chromosomes that are determining what gender we're going to be? So humans have 46 chromosomes. We have 23 pairs, which means that our 2n number is 46. So 2n is equal to 2 times 23, which gives us the 46. Remember, n is equal to one set of chromosomes from each parent. So we get 23 from mom, we get 23 from dad. So n plus n gives us 2n. We have in that one pair of sex chromosomes, which could be X or Y, that actually determine the sex of the individual. And then we have 22 pairs of autosomes, or what they refer to as body chromosomes. So the body chromosomes or the autosomes are all of the other chromosomes, and then we have that one pair that actually determines the sex, if you're going to be male or female. Remember, homologous pairs of chromosomes means that one comes from mom and one comes from dad. So for our copy number 1, one came from mom, one came from dad. So we have 2. Chromosome 2, one came from mom, one came from dad. So we have 2. Chromosome 3, one came from mom, one came from dad. So we have 2. And that's true for all 23 pair of chromosomes that we have. So in a human female, we have 22 autosomes. There are 22 of those body chromosomes, plus one sex chromosome that came from the mother in the egg. There are 22 autosomes plus one sex chromosome that came from the male in the sperm to give us a total of 44 autosomes plus 2 XX sex chromosomes for a total of 46. 44 plus 2 is 46. In a human male, we have 22 autosomes plus one sex chromosome that came from mom in the egg. We have 22 autosomes plus one Y sex chromosome that came from the male in the sperm to give 44 autosomes plus 2 XY sex chromosomes to give us a total of 46. So again, 44 plus 2 is 46. So the difference then isn't in the autosomes. The difference is in the sex chromosomes. A human female has XX, a human male has XY. So how would we complete a Punnett square for that? What would we do? Well, if I took the possibilities from the female can only give, remember, X or X. The male can give X or Y. So you set the Punnett square up the same way, and we bring them in to show what goes in what direction. So each time parents try to have children, there's a 50% chance of a boy or a girl. And this shows you, using a Punnett square, this shows you why it's a 50% chance. So if you're asked the question, which parent actually determines the sex of the offspring? Which parent determines the sex of the baby? And it's definitely the dad, because we can get an X or a Y in the sperm. We can only give X from the egg. So then, how many X or Y sperm does a male human have then? Well, it's about 50-50. So in any sample that you might have, you would have 50% that would have the X chromosome, and you would have 50% that would have the Y chromosome. So when it comes out, we have a 50% chance of a girl and a 50% chance of a boy every single time people try to have a baby. So sex determination is a relatively simple thing to think about, and it makes sense that, okay, we have differences in males and females, so it has to come down to the DNA. And if you have 2 X chromosomes, then you're a female. If you have an X and a Y, then you're a male. Well, how do those chromosomes fall in like all the other chromosomes do. They must have genes on those chromosomes or there wouldn't be chromosomes, because remember, the chromosomes make up the genes. So what happens is they started looking at something known as sex-linked traits. In other words, it involved genes that are carried on the X chromosome only. So it's on that 23rd pair. The Y chromosome is lacking DNA. It's not as big. If you look at a picture of a Y chromosome, it's smaller than the X chromosome, and it doesn't carry the genes for the traits that the X chromosome has. Therefore, the male only has one allele for these traits. Remember the allele, like if I had big T and little t, those were my alleles for the T gene. Those are the different options, dominant or recessive. Well, in a human male, they only have one copy of the genes on the X chromosome because they only have one X chromosome. The Y chromosome doesn't have that corresponding gene to match up. Females who are heterozygous we call carriers because they don't have the trait, but they can pass it on to their offspring. So they're carrying that recessive trait with them. So when we talk about the difference between an X and a Y chromosome, if you think about it for a minute, can information critical to the survival of a human being be on the Y chromosome? And I'm hoping your answer to that question is no. But then we have to explain why. Why is it that no information critical to the survival of a human could be found on the Y chromosome? And that's because females don't have a Y chromosome. If the information was critical to survival, if you had to have that information to survive, then females wouldn't be alive because we don't have the Y chromosome. So what is the information found on the Y chromosome? It's information essentially to make males into males as they're developing as embryos and into fetuses so that they end up being a human male. So that's the information that for the most part is found on the Y chromosome. Okay, so what does this look like if we actually try to do one of these crosses? Well, let's talk about phenotype, remember the physical trait, and the genotype, the genetic makeup. So our key that we're going to set up looks a little bit different because remember we've got to keep into account that females have two X chromosomes and males don't. So in a normal female, on my X I would have a big N telling me normal. On the other X I would have a big N. So completely normal. A carrier female, I would have the X with the big N, again normal, and X with the little n telling us that it's diseased. In the diseased female, I would have X little n, implying that both of them had or were carrying that disease trait. In the normal male, I would have X big N, Y, and then the diseased male, I would have X little n, Y. Again, remember, the male only has one copy. So can there be a carrier male? No, there can't be. They either have it or they don't. So how do we do the Punnett square? Well, let's just say that the mom, the female, was a carrier. She was heterozygous. So I've got X big N, X little n, and let's say that dad happened to be normal. So X big N, Y. So we complete the Punnett square exactly the same way. But then the question becomes, of the females, so of the females, XXXX, 50% of them would be normal, 50% of them would be a carrier. So then of the males, XY, XY, 50% would be normal, that's this one here, and 50% would be diseased. So the question then becomes, who is more susceptible to having a sex-linked trait? And I hope your answer to that question is that the males actually are more susceptible to it. Why is that? Because they only need to have the one copy of that diseased condition to actually express it. Here, the female has the one copy, but She also has the normal or the dominant copy, so it overrides it and she doesn't express that recessive trait. So what are some examples of things that we find on the sex chromosomes? What are some examples of sex-linked traits? One of them is hemophilia. Hemophilia is a condition where you can't clot your blood, so potentially if you get a bruise or a little cut, you could bleed to death from that. Another one is muscular dystrophy. You may have heard different fundraisers that they do for people that have muscular dystrophy. It's where the muscles start to deteriorate and you lose control of muscles. And unfortunately, if you lose control of the muscles like your heart or your diaphragm, major muscles that keep us alive, then you can see where that could end poorly. Color blindness is an example of a sex-linked trait. That's why more males happen to be colorblind than females. And you say, well, yeah, but color blindness isn't really a disease. Well, no, it's not. But it is an example of a sex-linked trait. You would set it up the same way, and this is why more males are colorblind than females, because they only need to have one copy of that gene to express the color blindness condition. The female, if she has one copy, is a carrier, so actually expresses normal. And the only other one that I want to talk about is baldness. So you always hear, well, it comes from your mom's side of the family. And then a guy says, well, yeah, but my grandfather has a full head of hair, so I'm not going to go bald. Well, here's the thing. Your grandfather, right? Your grandfather could be normal, full head of hair. But you inherit from your mother that recessive condition. So regardless of what your grandfather had, you inherited this from mom. Therefore, you would express that condition of baldness, which again isn't a disease, but this is how they go through to say what those characteristics are going to be. So that gives you a couple examples of sex-linked traits. It gives you how to set up the Punnett square for a sex-linked trait, and it also discusses with you how to set up the key. The key is probably the most difficult part. The only other thing that you need to remember is when we talk about females, only half of these offspring are female. That's why of the two, one of them is normal, one of them is not. So it's 50-50. Of the males, one of them is normal, one of them is not. So that gives you some information about sex determination and sex-linked traits. Thanks for watching the video, and I'll see you next time.